Hello everyone, and thank you for joining us for today's webinar with Surface Measurement Systems. The title of today's session is Surface Energy Analysis for Measuring Physico-Chemical Properties of Materials. Today's session is being delivered by our very own application scientist, Dr. Sabia Ahmed. Dr. Ahmed is the application scientist for both DVS and IGC SEA at Surface Measurement Systems. She gained her master's degree in pharmaceutical chemistry at the Queen Mary University of London and her PhD in chemical engineering at the Imperial College of London. After her PhD, she started working for Surface Measurement Systems as our application scientist, and as mentioned, has worked extensively on both our absorption systems, the IGC SEA, and our DVS range. Just before we kick off today, I'd like to remind everyone that as well as today's presentation, you will have an opportunity to engage Dr. Sabia in a live Q&A session. So if at any point during today's presentation you have a question for the doctor, please feel free to submit it through the questions panel, and we will ask the question directly to the doctor in the live Q&A session at the end of the presentation. Or alternatively, if you have maybe a slightly long question, or you would like to ask the question yourself for any other reason, go into a bit more detail with the doctor, please feel free to raise your hand at the end of the presentation, and we will let you know when you can unmute your microphone so that you can ask the question yourself and get your response from Sabia. So without further ado, I would like to hand over to Dr. Sabia Ahmed for today's presentation. Thank you, everyone.
Thanks, John, for the introduction. I'm just sharing my screen now, so I hope you all can see it.
Yes,
lovely, thank you. So in today's presentation, what I'll be discussing is what's called Inverse Gas Chromatography Surface Energy Analyzer. So that's the IGC SEA. So I'll be going through a bit of the introduction and on what the system looks like and what it does, and then I'll go through a few case studies of some results. So inverse gas chromatography was first developed in the 1950s. It used gas phase molecules as a separation technique, and in 2009, Surface Measurement Systems developed what's called an SEA. This is Surface Energy Analyzer. This is designed to determine the surface energy and heterogeneity. But alongside this, we can also understand other properties of our samples, such as adsorption isotherms, heat absorption, glass transition temperature, and a few others, which I will go through too. So just comparing with standard analytical gas chromatography, usually in this case, we have a mixture of gas phase probes, which we would then inject into a column. And depending on the interaction with the column, these would then separate out. And as a result, on the detector end, what you're left with is peaks at different retention times. However, in inverse gas chromatography is a little bit different. So what we're doing is packing the column with your sample of interest, and then injecting individually a few probes with known properties. On the detector end, we will end up with peaks based on different retention times, and this is a result of the interaction between the probe molecules and the sample of interest. So this is what the typical IGC SEA system looks like. It has two drawers on either side and a door in the middle. When you open up each of the drawers, what you'll see is 6 places where you put your solvents. These are the reservoirs. So this is where you choose which solvents you wish to use for your experiment. The system comes with either a helium or nitrogen carrier gas. And when you open the door in the middle, what you'll find is where you put your columns. So we have a 2-position column, 1 and 2, and this is surrounded by a column oven. The column oven goes from 20 degrees to 150 degrees. We can also offer a background humidity controller. So in this case, what we're doing is applying humidity on the surface of your sample and then running your experiments. And in this case, one of our reservoirs will have to be water. The detector we use is a flame ionization detector, and this is really useful for measuring accurate concentrations of organic vapors. We also have some safety features as well. So we have hydrogen leak detectors and organic vapor leak detectors. The hydrogen leak detector is necessary for igniting the FID. Our system is quite versatile in terms of the different types of materials that we can analyze. So at the bottom, I have some examples such as cotton, carbon fiber, hairs, granules, and even medical metal implants. To prepare a sample for IGC-SEA, it's very different from the standard GC column. It's much more straightforward. So what we have is some silanized glass columns. What we effectively do is plug in some silanized glass wool. And in this case, we then funnel in our sample of interest and close off with some more silanized glass wool. So in this case, we don't have any of our material going into the lines of the system. So before starting an experiment, there's a few things you need to do. First is to pack a column with the sample of interest. Then go ahead and choose some probe molecules. So the most common property measured by IGC-SEA is surface energy. In this case, we need a few non-polar probes, and this gives rise to the dispersive interactions. We also need some polar probes as well, and this gives rise to specific interactions. We can then choose how to inject them. So we can inject them at very small concentrations, so infinite dilution, or much larger concentrations. We then start our experiment on the software, and depending on the interaction between the probe molecules and the sample, we would obtain different peaks based on different retention times, which we can go ahead and analyze. So the system comes with a variety of different probe molecules. Here we have some standard ones we have in our system, a mixture of some non-polar and polar probe molecules. Alternatively, if you wish to add one of your own solvents as well, we just need, it's relatively quite straightforward to calibrate onto the system. You just need a few physical properties and then you're good to go. We also offer another way to analyze samples. So instead of packing a sample in a column, you may have samples that are more planar. In this case, we have a film cell. So a film cell looks something like this. And you would place your planar sample in between these panels here. You then close off your film cell. And these lines here, they are directly linked to the IGC-SEA where your columns would go inside the door. And your probe molecules would be injected along this panel here. In this case, you need a sample that's big enough to cover this space. And because with this film cell, it would sit beside the IGC-SEA. So you may not necessarily have the temperature control, but you will have the humidity control, and you will be able to carry out exactly the same experiments. There's two different softwares we have with this system. One is a control software. So in this case, this is where you would manage and create your experiments. After you run your experiments, we can move on to the analysis software. And this is where you would have a look at your raw data and your different peaks and analyze those peaks and obtain different properties. So peak analysis is relatively quite straightforward. In this example here, we've injected a few non-polar molecules. We've also injected some methane. So this is to calculate the dead volume. This is as a result of one of our hexane peaks. What you do is simply select the beginning and the end of the peak and click calculate. And in this case, as you can see, all these parameters here will start filling up. So analysis is automatic. However, if you did want to kind of export some raw data and do some back calculations, that's also a possibility too. So there's a few things that we can measure with IGC SEA. One, the most common one is surface energy. And because we are injecting polar probes, we are able to understand acid-base interactions in terms of Ka and Kb. We are also able to understand and obtain isotherms, and as a result, we can then calculate the BET specific surface area. Other things we can measure work of adhesion and cohesion, and also because we're able to inject multiple concentrations, we're also able to obtain a heterogeneity map of the surface of the sample. So, like I mentioned before, surface energy is the most common property measured by the IGC technique. And what it is it's analogous to the surface tension of liquids. This the ability of the surface to react compared to the bulk. And in this case, we need dependent on two different components. One is a dispersive component, and this is in the form of maybe some N-alkanes. This gives rise to physical long-range interactions. We also need Lewis acid-base components, and this is in the form of your polar probes, and this gives rise to chemical short-range interactions. So before we start a surface energy experiment, there's a few things we need to know. So one of which is the BET surface area. So we can calculate the BET surface area using our IGC SEA. Alternatively, if you do have the value at hand using other methods, we can also just plug in that value too. What we also need to know is the size of our probe molecules. So as I showed before, we have like a nice database of the probe molecules available calibrated in our system, and we also have their physical properties. So these are the two things we need to know. So what we then can go ahead and do is use a software to calculate the amount of moles or percentage of the probes that we need to obtain and achieve a certain coverage of the surface of your sample. Then we can go ahead and start the experiment. And as a result of the interaction between the probe molecule and the sample of interest, you will have different interactions based on the different types of probe molecules, and as a result, different retention times and volumes, which we can then go ahead and analyze. So surface energy is quite an interesting property because it actually can be related to other properties, one of which is wettability. So if increasing surface energy, you would also get increase in wettability. You also get an increase of cohesion. So this is how likely the particles are likely to interact with itself. Because we can inject multiple concentrations, we can have an understanding of the heterogeneity or the homogeneity of the surface of the sample. So if you have any defects or surface porosity, it's useful for analyzing these surfaces. We can also calculate work of adhesion. This is to unlike materials that you'd wish to go ahead and calculate the work of adhesion between the two. I'm going to go through a few case studies, one of which is looking at analysis of D-mannitol and understanding its heterogeneity. So for this example, we have D-mannitol and we have silanized D-mannitol. And this is the resulting plot that we obtain using the IGC SEA system. This is looking at the dispersive surface energy. So this is a result of our non-polar probes interacting with the surface of the sample. And on the x-axis, we have surface coverage, increasing the surface coverage across the sample. So there's a few things that we can see here. One of which is that our silanized sample has a much more lower surface energy compared to our untreated D-mannitol. What we can also see is the shape of the profile. For silanized mannitol, we have a very linear profile, and for the untreated D-mannitol, we have quite a curved profile, especially in this region here. So what this is telling us is that at infinite dilution and very small concentrations, the molecules are actually small enough to interact with high energy sites in the sample. And as a result, we have a high surface energy for untreated D-mannitol. However, when we start to silanize the material, silanization has caused these areas to be blocked. In this case, we lose this area of surface energy, and that's why we have a more linear plot in this case. Another way that we can understand the sample is by taking a point-by-point integration and plotting that. And as a result, we obtain a dispersive surface energy distribution. So we're looking at the minimum, the maximum, and the gamma D50. What we can interpret from this plot is that the wider the peak width, the more heterogeneous the sample. And the more narrow the peak width, the more homogeneous the sample. So you can see that salinization has actually changed the material to something that's very heterogeneous, to something that's very homogeneous. We can also relate this to flowability properties. So with the as received D-mannitol, what we're seeing is that we have very unstable flow behavior. In this case, we're looking at different air velocities. And at very low air velocities, we have very unstable flow behavior for D-mannitol, which we don't see for the silanized material. And this is due to the higher surface energy correlating to higher work of cohesion. And this can have a poor effect on flowability. However, as you increase the air velocity, you're actually overcoming this cohesive effect and therefore have a much more stable flow. With the salinized D-mannitol, the salinization has actually caused to have a quite constant and quite reliable flowability across the sample. In the next case study, we're looking at some pharmaceutical drugs and excipients. So we're looking at the drugs budesonide and salbutamol sulfate. The excipient we're looking at is alpha-lactose monohydrate. We wanted to use the IGC-SCA to understand kind of content uniformity of the individual components, the drugs and the lactose. So this is a result of the dispersive surface energy of each of our materials. And what we can see is that the budesonide has a higher dispersive surface energy than the other two components. What we can also plot is the work of cohesion and adhesion. So in this case, we want to understand the affinity between the excipient and the drug molecules. So what we have is, if we want to look at the blending for the lactose and budesonide, what we first can look at is the lactose cohesive properties of itself and the budesonide cohesive properties of itself. What we can see when we compare these two is that budesonide has a stronger affinity to interact with itself, and this will cause higher aggregation compared to our lactose and lactose. So in this case, we would have a weak affinity between the drug and the carrier, and we would expect quite poor blending performance. However, when we looked at the lactose and salbutamol sulfate, we actually see that the work of cohesion for the salbutamol sulfate with itself is much lower compared to the lactose and salbutamol sulfate, which is quite higher. So this again is suggesting that we may have a stronger affinity between the drug and the carrier, and much more blending performance with our lactose and salbutamol sulfate. The next example here is looking at the influence of bleaching conditions on some hair samples. In this case, the different hair samples that we're looking at are untreated chemically bleached samples, UV treated samples. And we've preconditioned the samples for 5 hours. The experimental temperature was 303 Kelvin. We didn't apply any relative humidity, and we had a stable flow rate of 10 ml per minute. So in this case, to calculate the dispersive surface energy, we injected alkanes from tridecane to heptadecane. And this, we also had a look at some other probe molecules. So we calculate the free energy with a hexanol probe and a butyl acetate probe as well. So this is the results obtained. And as you can see here, by looking at the dispersive surface energy for the untreated hair sample, we have quite a lower dispersive surface energy. So this is indicating a more homogeneous sample. However, when we start to bleach the hair or treat it with UV, you get quite a higher dispersive surface energy. So this indicates introducing a bit more heterogeneity to the surface of the sample, which is what you would expect if we are treating hair with quite harsh conditions. We can also understand the free energy between the samples and hexanol and butyl acetate. And again, what we can see is that we have a smaller interaction with our untreated sample and a higher interaction with our bleached and UV treated samples. What's also interesting is that the different types of treatments, so we have bleached and UV. However, what we're seeing is that the interactions and the surface energies are actually quite similar. So they actually have quite similar effects to each other. So the next example I'm looking at is going to talk about is the characterization of a drug and a PLA material, so that's polylactic acid material. So this was used to characterize 3D printing for drug-loaded implants, and we're looking at disulfiram drug and the polylactic acid. So polylactic acid is quite useful as it can offer a formulated drug release over a duration of days. And in this case, we're looking at two processing conditions. So the PLA plus the drug, which has been cooled during formulation, and the PLA and the drug, which has been non-cooled. We want to understand the differences of these two processing conditions. So what we have here is the dispersive surface energy with our increasing of surface coverage of our cooled and non-cooled samples. So what we can see first is that we have quite a curved profile. So this is telling us that our sample is quite heterogeneous. We can also see how similar these two are. So in terms of heterogeneity and dispersive surface energy, these are two samples are quite similar. This plot looks at the specific surface energy across increasing surface coverage. So in this case, what we can see first of all is that it's a lot lower than our dispersive surface energy. So our dispersive surface energy contributes to a much more major part of surface energy. What we can see is that the cooled material has a slightly higher specific surface energy than our non-cooled material. What we've also then gone and done is calculate the specific free energy. So we've injected dichloromethane, ethyl acetate, chloroform, and toluene in this case. And what you can see is in the interaction of our non-cooled material and our cooled material with all these probe molecules. So what we can see is that for both samples, the dichloromethane has a much more stronger interaction with the samples. And in this case, what we can understand from this is that there must be some labile functional groups on the surface of the samples that are responsible for a stronger interaction with dichloromethane. What we can then also do is calculate the Ka and Kb for the surface of the samples. And what we can see is that the cooled sample, we can see a general trend of smaller Ka and Kb Ka compared to Kb. And we can see that the cooled sample has a higher Kb. So we can say that this is more basic in nature than our non-cooled sample. So it has more electron donating groups on the surface of the sample. So in this next case study, we're looking at the surface energy heterogeneity of carbon fibers. In this case, we're looking at sized fibers and unsized fibers. We are also looking at the pre-treatment conditions at 30 degrees and 120 degrees. So in the IGCSE system, we can purge the material prior to any experimental analysis. And this would be the preconditioning step. So we can precondition the samples directly before we start an experiment. And in this case, we've pre-treated at 30 degrees and 120 degrees. And we just want to understand if this has a difference and if the sized and unsized carbon fibers contribute to a difference in surface energy. So this plot is looking at the dispersive surface energy with increasing coverage. So what we can first see here is that our sized material compared to our unsized material has a lower dispersive surface energy. Our unsized material has a much higher surface energy, especially at this region here, infinite dilution region. And this is suggesting that at small concentrations, we're able to access higher energy sites, which are only available in the unsized carbon. But once we increase the injections over higher surface coverages, these tend to plateau out. So this is suggesting that the unsized material are much more heterogeneous compared to our sized material. We've also done a point-by-point integration to obtain the dispersive surface energy distribution. What we can see is that the wider the peak width, the more heterogeneous, and the more narrower the peak width, the more homogeneous. So in this case, if we have a look at the temperature differences, we can see that once we increase the temperature of our carbon fibers to 120, what this is doing is actually removing any kind of adsorbates or anything blocking high energy sites, exposing these energy sites when we do our experiment. So at 30 degrees, this isn't enough energy input onto the surface of the samples, and we cannot remove these adsorbates. And as a result, if we look at these two peaks here, we have a much more wider peak width at 120 degrees and a much narrower peak width for 30 degrees. We can also have a look at the effects of surface treatment. So an oxidized sample, oxidized and sized with epoxy agents, and comparing it to an unoxidized and unsized material. And this is the resulting Ka and Kb plots. So what you can see is due to oxidation, we have a higher Ka for our material. And this is, of course, what you would expect compared to our reference material. And our reference material has a much higher Kb, more electron donating groups on this sample here. And we can also see the effects of different types of oxidation as well. So the final case study that I'm going to go through is looking at the interaction with polymer matrix. So in this case, what we have is carbon nanotubes. So we have, as received carbon nanotubes, we have carbon nanotubes oxidized with carboxylic acid functional groups. We also have some nanoclay, as received nanoclay, and nanoclay functionalized with isocyanate groups. We also have a our polymer matrix. So this is polyurethane matrix. So this is looking at the total surface energy of each of our components. And what we can see is that we have a higher total surface energy of our adhesive nanoclay and our carbon nanotubes with carboxylic acid groups. So this can give an indication of these two samples having a higher particle-particle interaction. And this is quite important because once we start to blend into the polyurethane matrix, it can give an indication of a more these two materials having a much more poorer dispersion into the polyurethane matrix due to this higher total surface energy contribution. We've also calculated the work of adhesion and cohesion and calculated the adhesion-cohesion ratio. So in this case, it's a good indication of the balance of forces between the adhesion and forces of cohesion. And this is quite important in formulation studies because if you have too weak or too strong particle-particle interactions, this can either lead to like segregation or aggregation of the material. And this can lead to maybe poor dispersion into the polymer matrix. So it can be used as a formulation tool prior to making any final products. And we can develop and optimize the work of adhesion and cohesion ratio. We've also coupled this with another technique to understand the mechanical performance, and it's showing that with the higher work of cohesion, we have higher tensile strength. So it's very useful to kind of correlate the data from the surface energy to work of adhesion and cohesion to other mechanical properties. So just to summarize, the surface energy analyzer is a very versatile technique. Can be used to understand several different properties of the sample. It's a vapor absorption technique, and we can characterize a variety of materials such as powders, fibers, films, and we can also understand subtle differences in surface chemistry and use it as a formulation tool as well. So I hope this has been useful for you. And if you do have any questions, I'm happy to answer them.
Thank you very much, Sabia. Yes, so just a reminder to our audience, you can submit your questions through the questions panel, or if you would like to unmute your mic and ask the question yourself, please raise your hand and we'll pass it to you at the time to ask. So just the first question here, Sabia. Someone asks, is it possible to use some other solvents with the ITC system apart from the ones in the solvent database list? For example, some fragrance like alpha-pinene.
Yes, we can do that. So with the SCA, apart from the list that I've shown, to accommodate any other solvent, really you would need to fill out a few of these properties here. So molecular weight and liquid density. If you have the Guttman acceptor number and donor number as well available, it will be very useful. We have calibrated some fragrance molecules into our system, and the calibration is relatively quite straightforward if you have the known properties at hand.
Great. Question from Michelle Rodriguez. They ask, how much is this technique sensitive to the differences in column packing?
So with regards to column packing, we do have on our control software a pressure drop. So if you are packing the sample quite tightly, before the experiment, you would be able to see that once you put the column into the column position, it will then flow through the carrier gas, and it'll give an indication if the pressure is okay, or if you do need to maybe use a slightly larger column, or separate out the sample within your column. And if you do choose to separate out the sample, we have done some column-to-column reproducibility studies, and it doesn't affect the results if you do use maybe some silanized glass wool in between to adjust the pressure. So we have done some column-to-column studies, and this doesn't affect the results.
Great, thank you. A question here from Moshem Gao. They ask, how much sample should you be using for an ITC experiment?
So the sample is typically based on the BT surface area of your material. So if you have quite a low surface area material, about 1 meter squared per gram, you may need about 500-600 milligrams of your sample. However, if you have a sample which has a slightly higher BT surface area, so about 100 meters squared per gram, you would need roughly about 10 milligrams. So it does depend on the rough estimate of the BT surface area.
Great. Another question we have here is, what are the mass requirements?
Sorry, John, you were breaking up there, I couldn't hear you.
Apologies. The question is, what are the mass requirements for sample analysis?
Yeah, so similar to what I said before, it does depend on the BT surface area of your sample. You need more mass for a low surface area sample, and high mass for a high mass for a low surface area sample, and a low mass for a high surface area sample.
Great, thank you. We did have a by Jack Nottingham, but he lowered his hand, so it might be we addressed what he was going to ask already. But while I ask another question, Jack, if you would like to ask a question, please raise your hand again, and I'll go to you after this next question. So before that, our next question is, how does this technique compare with other techniques that measure surface energy, for example, the contact angle?
So with regards to contact angle, you can compare the surface energy results as long as you're using the same types of probes. So the same polar probes and non-polar probes. However, with the contact angle experiment, you're kind of limited to the probe molecules, and also you're only looking at localized areas of the surface of your sample. Whereas with the IGC-SCA, we can actually inject different percentages across the surface of your sample. So we are able to look at the whole sample rather than small localized areas. So it's much more representative of how energetically stable and the surface energy is on your sample compared to contact angle.
Great. A question here from Claudia Arnold, and we may have covered this before, but I think this goes into a bit more detail. So we've covered before that it gets sensitive to column packing differences, but this question asks, does the packing density pressure drop along the column influence the results? Can you correct for it, or is it necessary to achieve a certain pressure drop when preparing the column?
Sure. So when preparing the column, once you prepare the column and you place it into the column position, before running your experiment, the system will run a constant flow of your carrier gas. And if you do see quite a large pressure drop, around 800 torr, then the system will, you'll have a message on your system telling you that you need to pack the sample more loosely. So in this case, there's a few ways to overcome this. We have different column sizes. We have 2, 3, 4, and a 10mm column. So you can increase the column size. Alternatively, if you have quite a quite high larger column size, what you can do is insert some silanized glass wool between your sample packing. So this will reduce the pressure, and because it is silanized glass wool, it doesn't interact with any of your experiments. And then we have a nice separation between your sample. Yeah, so once you do run your experiments, we've done some studies from column to column reproducibility studies, and we haven't seen any difference in the results.
Okay, great. And I think we have time for a question here. Jack Nottingham has kindly typed his question in. Now, just an advanced apology if I don't get all this question right, because I am not quite scientifically minded as most of the people listening to this. So I'll need to read this yourself as well after I read it to you, Sabia.
Sure.
How do you get dispersive Gibbs-free energy from the retention time and peak area? I assume you are calculating Gibbs energy from the surface tension using D equals YDA, which is surface energy and surface tension. Yeah, surface and surface tension, which assumes the adsorbent is forming a thin film. Can you elaborate on how dispersive energy is calculated?
So with the dispersive surface energy, we inject different non-polar probe molecules, and in this case, we create a linear plot. So if I go down to this slide here, we have an RT-LNV plot, and based on this linear plot, we are able to calculate the surface energy. And with regards to delta G of the specific probe molecules, we take this linear plot and we plot the delta G based on relative points along this plot here. So that's the way that we calculate the dispersive surface energy as well as the Gibbs free energy. If it's useful as well, we can also send you a nice PDF of how we go into detail on the equations that we use to go ahead and calculate as well.
Well, thank you, Sabia. I think that's all the questions for today, and that takes us quite neatly up to the end of our time. So thank you once again so much for giving this presentation and sharing those insights with our audience. Do you have any final thoughts before we go? Doesn't sound like it. So yeah, so that brings us to the end of today's presentation. So again, a big thank you to all of our attendees for taking part, and another big thank you to Sabia for being here today to share her insights with us. So thank you all for today. We do have a full range of events being posted on our website later this week, so we invite you to check back at www.surfacemeasurementsystems.com later this week to see more of the virtual webinars and workshops we have coming up in the next month or so. So thank you all once again for joining us. I hope that wherever you are, you have a wonderful morning, evening, or night. Thank you.
Thank you, everyone.